Imagine you're riding in the passenger seat of a fully self-driving car gliding through a quiet neighborhood just after dawn. The world feels still, peaceful, gentle. The street is the kind of place where sunlight cuts through trees in long golden blades, where the lines on the asphalt shimmer slightly, where you can hear the soft hum of tires, and nothing else. Then something unexpected happens. Ahead of you, there's a delivery truck parked exactly where no one would expect it, half on the road, half in the shoulder, in a position where the car's lane narrows to a tight choke point. A human driver doesn't even think about what comes next. They nudge gently left, giving the truck space, then ease back to center. But for a self-driving car, this moment is terrifying. Not because it can't see the truck, not because it can't steer, but because, despite millions and millions of examples of expert driving, it still may not know what to do. And that single moment, that tiny deviation from the perfect, ordinary world, is exactly where self-driving systems so often fail. That moment is the beating heart of the research we're exploring today. A paper that dares to say that 30 million expert driving examples still aren't enough, and that the only way to teach a car to drive like a human is to also teach it what happens when humans don't. This is the story of ChauffeurNet, a system that learns to drive by imitating the best and synthesizing the worst. If you want more deep, cinematic explorations of world-changing research like this one, hit like right now, subscribe to the channel, and turn on notifications. It genuinely helps us keep producing content like this, and it tells the algorithm that people actually want long-form, high-quality explanations of cutting-edge AI. Now, let's start the engine. To understand what makes ChauffeurNet special, we have to start by understanding a surprisingly deep problem at the core of how we usually train autonomous driving systems. Most modern end-to-end learning projects try to predict driving actions, steering, braking, throttle, directly from raw sensory input like camera images. The idea is seductive. Just feed the neural network all the pixels and let it figure everything out. But the researchers behind ChauffeurNet took a different path. They decided to sidestep the noisy ambiguity of raw sensor data and focus on something more structured, more informative, and much more controllable: a clean bird's-eye view map of the world. Instead of giving the model camera frames and asking it to guess how the world works, they pre-process all the raw sensor data through a separate perception system. The output of that system gets drawn as a 2D top-down image composed of intuitive layers: road lanes, curbs, sidewalks, crosswalks, traffic light states along the lane centers, speed limits, the intended driving route, bounding boxes for vehicles and pedestrians, and even a fading trail of where the ego car has been. It's like the neural network is looking not at the pixels of reality, but at a beautifully drawn diagram of exactly what matters for driving. And from this diagram, ChauffeurNet doesn't output steering commands. Instead, it predicts a trajectory, a future sequence of positions, headings, and speeds the car should follow. A separate controller then turns this trajectory into actual steering and throttle changes. This mid-to-mid architecture massively lowers the difficulty of the learning problem. The car doesn't need to learn what a red light looks like. It doesn't need to decode lane paint from shadows. It doesn't even need to understand how to convert a desired turn into real steering movements. All of that is handled by other systems. ChauffeurNet's job is simply to say, here's where the car should be for the next few seconds. That's the plan, that's the execution. And yet, even when the researchers trained this system using 30 million examples of expert human driving, it failed in shockingly simple ways. So what went wrong? At first glance, nothing. When tested using the typical method, open-loop evaluation, ChauffeurNet looks fantastic. Open-loop testing basically means take log data from real human driving, feed it into the network, and compare the network's predicted trajectory to what the human driver actually did. If they line up well, the network is good. And ChauffeurNet did line up well. But the moment they put it into a real simulation where the model's output determined what happened next, everything began to fall apart. The car would drift slightly from the center of the lane. That drift would compound. The car would approach a parked car and, despite having 30 million examples of humans passing parked cars, plow straight into it. Worse, the model couldn't recover from even the tiniest deviation. If its position or heading was even slightly different than the expert's, it was lost. Why? Because the expert data never includes mistakes. Humans don't intentionally drive halfway onto the sidewalk. Humans don't point the car 20 degrees off the direction of the lane. Humans don't drift dangerously close to a parked vehicle. So the model never sees any of these states during training. And if the model never sees them, it never learns how to handle them. It's like teaching someone to ride a bicycle using only perfect, stable, smooth, flawless riding examples. Then, on their first real attempt, they wobble an inch and instantly fall over because they were never taught how to balance. This failure mode is at the heart of imitation learning for driving, the distribution shift problem. Once you're off the demo path, you're on your own. This is where the key insight of the ChauffeurNet paper appears like a plot twist. If the model can't learn how to recover from mistakes because the expert never makes mistakes, then we must create those mistakes. The researchers do something wonderfully counterintuitive. They take the pristine expert trajectories and deliberately warp them. They pick a point in the middle of the trajectory, usually around the halfway mark, and apply a random spatial and rotational offset. Sometimes they shift the car half a meter to the left or half a meter to the right. Sometimes they rotate the vehicle tens of degrees off the correct heading. Sometimes these synthetic trajectories cause the car to veer off the road or collide with obstacles. The researchers don't remove those examples, they keep them. And then they fit a smooth curve that starts where the human started, detours through the perturbed position, and returns to where the expert ended up. This single act, this intentional sabotage of the human trajectory, gives the model something it never had before: knowledge of what the world looks like when things go wrong, and most importantly, knowledge of how to get back to where things go right. They call this synthesizing the worst. And this moment transforms the training process completely. Suddenly, the network isn't just learning how to follow a perfect demonstration. It's learning how to recover from adversity, how to correct drift, how to recenter the car in the lane, how to steer around obstacles even when its own previous decisions put it in a dangerous position. It learns resilience. But synthetic errors alone aren't enough. The researchers also add new kinds of loss functions, new behavioral penalties, that teach the network the meaning of safety. They give the model a collision loss, which penalizes overlap between the predicted future bounding box of the ego vehicle and any detected object. They give it an off-road loss, which penalizes any overlap between the car and non-drivable space, like curbs, medians, grass, and sidewalks. They give it a geometry loss, which gently encourages the predicted positions to stay aligned with the smooth curve of the intended route. And to help the model understand the behavior of other road users, they add auxiliary prediction tasks, a road mask predictor, which learns to infer where the drivable area is, and a perception RNN, which predicts the future movement of surrounding vehicles. These tasks share the same underlying features as the main driving network, meaning that every parameter update improves the model's understanding of not just the ego car, but the whole scene. It's like teaching someone to drive while also teaching them to predict where other cars are going and how the road is shaped. When you do that, their driving gets better. Still, there's one more twist. If imitation loss, meaning match the expert exactly, is always active, the model becomes too rigid. It becomes unwilling to deviate from what the human did, even when the human's exact path is impossible due to the artificial perturbations. So the authors introduce imitation dropout. On some training examples, the imitation losses are turned off completely, leaving only the environmental losses, collision, off-road, and geometry to guide learning. In these moments, the network isn't told to copy the human. It's told, find any trajectory that avoids crashing, stays on the road, and follows the route. This gives the model the freedom to improvise safe behavior. And with all of these ingredients working together, perturbed data, environment losses, auxiliary tasks, and imitation dropout, the neural network finally becomes something more than a mimic. It becomes a driver. To see how profound the transformation is, the authors test the model in simulation with several challenging scenarios. In one scenario, the ego vehicle approaches a parked car that partially blocks the lane. The simplest imitation-only network either crashes into it or stops behind it and freezes. Variants that include perturbations, but not the right losses, still behave poorly. But the full ChauffeurNet model, trained on synthetic mistakes and guided by environmental constraints, nudges left, glides safely past the obstacle, and returns to its lane. In another scenario, the car begins misaligned, already drifting from the lane center. The basic model cannot recover. ChauffeurNet does. In a third scenario, a slow-moving car travels ahead of the ego vehicle. ChauffeurNet slows down smoothly, maintaining a safe follow distance, and doesn't attempt to pass unless appropriate. It's not perfect. Sometimes it gets over-aggressive in rare corner cases, but it is orders of magnitude more robust than any version trained purely through imitation. Then comes the ultimate test, putting ChauffeurNet in a real car. When integrated into the full self-driving stack, with real perception feeding it bird's-eye renderings and a controller executing its predicted trajectories, the system successfully handles real roads, real intersections, real stop signs, real turns, and real interactions with pedestrians and other vehicles. It drives smoothly for long stretches without drifting, without freezing, and without the catastrophic failures seen in earlier models. This is remarkable. Remember, this model has never explored the real world through reinforcement learning. It has never been corrected by a human in real time. It has never been exposed to autonomous driving mishaps. Everything it knows about recovery, danger, drift, collision risk, and safety comes from synthetic perturbations and smartly designed losses layered on top of 30 million human demonstrations. And that leads us to the deeper message behind ChauffeurNet. Sometimes, to learn how to do something safely, you have to learn from mistakes, even if you have to invent those mistakes yourself. Pure imitation learning gives you a brittle system that follows demonstrations only as long as everything goes perfectly. But by adding a controlled form of artificial failure, you transform imitation learning into something more powerful, a system that knows not just how to succeed, but how to succeed after things go wrong. That's what humans do naturally. And now, through clever engineering and clever modeling, that's what ChauffeurNet learns to do as well. If you enjoyed this deep dive into one of the most interesting papers in autonomous driving, make sure to hit like, subscribe, and comment below with which research paper you want me to explore next. Your engagement genuinely helps shape the direction of this channel and keeps these long-form breakdowns possible. Thanks for watching, and I'll see you in the next video.